If you subscribe to the channel, you'll get lots of interesting videos like this one. And if you like the video, it'll really help us out. Please comment down below for any other interesting things. That also really helps us out as well. Hi, and welcome to another edition of Easy Theory. So today we're going to probably have a long video, and we're going to look at a lot of the things that we've been doing in algorithms, all this recursive techniques, and we're going to talk about something that's actually really fundamental to algorithm design, which is first, asymptotic notation, and something that a lot of students learn about, which is the master theorem, which is related to this asymptotic analysis of algorithms, which is actually quite cumbersome if you just stare at it, but if you look at the idea behind it, it's really simple. So in order to start talking about this, we need to talk about asymptotic analysis. Okay, so the entire purpose of asymptotics is to get rid of all the unnecessary details of like how fast an algorithm actually works and just see what is the general trend. Is it going up really quickly in terms of how long it takes or whatever? Or is it going much slower or whatever? So the idea, as I said, is to remove the, quote, unnecessary details of how the algorithm works. So if the algorithm does a few operations, like 5 versus 10, it doesn't really matter. It's just twice as much. So what we're really focused on here is not necessarily comparing two algorithms in terms of their absolute performance. One is X better than the other one, but rather their relative performance. So it's not like we have, let's say we are plotting the size of the input that's given and the runtime on the other axis. So let's say that we have algorithm A taking looking like this, and algorithm B looking like this. Maybe I should put an arrow on the A. So we're not really focused on what this gap is here. The actual absolute difference between them, but we're going to look instead at the relative difference. So the question that we're going to try to answer is, what is happening in everything? What is happening with the relative difference between A and B? So from this picture, I can't really guarantee what's going to happen. Maybe A at this point is going to shoot to the moon, or maybe B shoots to the moon and then maybe cross or something. But maybe, for instance, A will, well, let's just say I happen to know that A will always be twice as big as B. Well, then the relative difference isn't getting any bigger because A is always going to be twice as much as B. But if at some point A was going to get closer and closer relative to B, that may be something we want to know. Or maybe the relative difference between them always will be growing. It'll never stop growing. But another thing to also keep in mind is we could have A, after this point, do some wonky bits right here. And so it's going to be uniformly going up. But what we want here instead is that after some, maybe a different color, let's do pink. After some cutoff point, where basically at this point, all bets are off in terms, or actually I guess all bets are on, in terms of the relative difference always going to be either growing or staying the same or going down after a certain point. And if you take this class, we usually refer to this as N0. So what we can say is if the size of the problem is at least N0, where N0 is just some number, it's just some fixed number, then the relative difference will keep doing the same thing. And what do I mean by that? It's not that like the relative difference goes down then back up and down and back up or whatever. It's either going to keep continuing to go up, or it's going to keep continuing to be the same, or continue to keep going down. It'll never fluctuate. Okay, and so that's what we mean by an algorithm comparing two algorithms. So what are some notations here? So what I'm going to say here is that f of n is going to be the runtime, and it doesn't have to be runtime, it's just something that you're measuring on the algorithm, maybe how much space it takes, but usually it's time. The runtime of A on input of size n. And I already need to be careful about this because I can't just say runtime, because in some cases the algorithm might be super fast, or in some cases it might be really slow. So what we mean here is something called worst case. So worst case, what is the absolute worst thing that can possibly happen on any input of size n? Okay, so like for Quicksort, for example, if I pick a bad pivot, then the runtime becomes n squared, essentially. But if the runtime, if it's not the worst case, it might be even lower than this. So, and for Quicksort, it actually is lower than that. I won't say what it is yet. And let's say that g of n is the same thing for b, the algorithm b on inputs of size n. Okay, so f is the runtime, or whatever you want to measure, for a, the worst case, and g of n is the worst case for b. So then, what do we want to look at here? So let's make our little plot again. And let's say that a is going up like this, and b is going much slower. So let's say that from this, we can conclude that the relative difference for A versus B is growing. And maybe I should put some arrows on. You got to make the picture pretty. So let's say that the relative difference between these two algorithms is growing. A is growing faster than B. So then what we're going to note here is to say that, I'll use white. So let's say, for this, we're going to say that g of n is big O of f of n. So big O, what does that mean? That just means less than or equal to. So g of n is less than or equal to b than a, because b is always less than a. Okay. There's an equal to because this is just the notation that's used. If you want a strict inequality, what you can say is little o f of n, and that is strict inequality. Okay, so if you want strict inequality, use little o. If you want less than or equal to, because sometimes you can't guarantee that it's not equal, then use big O. Okay. The other case may be that, and actually one other thing I should mention is that if we reverse the two, f of n is, well, it's not big O of g of n because it's bigger than g of n is. So what we use there is something called big omega of g of n. And what that is the exact opposite. It's greater than or equal to. And just like before, if you want a strict inequality, then you use little omega of g of n, and that means strictly bigger than. Because we can see here that f of n, which is this plot for A, is strictly bigger than this one, in this particular case. And as always, we need to formalize this. I'm not going to do it here because there's really not a point, and there are the whole point of taking a class is to look at a formal definition for this. I'm just looking at an intuitive explanation. There's some point n0 for which this becomes true. So when I say this means at some point this eventually becomes true, and not necessarily before. But it's not true for all n, it's true after a certain point. Okay. But another scenario might be that we have them being exactly the same relative difference. So let's say that A is going up again, and let's say that B is half of A. So yeah, let's actually write that down. So let's say that f of n is twice g of n for all n. Or maybe not for all n, but after a certain point it becomes 2. It doesn't have to be exactly this, it's just that it's some constant independent of n times g. Then what we say here is that f of n is big theta of g of n. And what this means is that the relative difference is in some sense equal. So that means that it's some constant times g of n always. And another way that you can actually think of this is that if you say that f of n is theta g of n, then this is exactly the same thing as saying that f of n is big O g of n, so it's less than or equal to g of n, and it's at least as big as g of n. So in some sense that f of n and g of n are exactly the same. One grows exactly the same rate as the other in terms of the relative difference. The one may be growing more, it may be always bigger. It's not that they're exactly the same plot, it's just that they're growing in the same direction. And the relative difference doesn't grow beyond a constant. The relative difference can change, but it's not going to continually go up or continually to go down. Okay? So that's what we mean by big O of everything. Okay, so where are we actually going with all this? So here we're going to be talking about the asymptotic runtime. And you may be thinking, well, isn't that exactly what you just talked about? So we use a slightly different notation for algorithms. So what we were doing before here was just talking about how fast functions grow. This is specific to algorithms. So what we note T of n to be is to be the runtime of some algorithm on inputs, and of course this is also worst case, on inputs of size n. Okay, and you may be thinking, well, isn't that just f? It's just that, or g of n, this is just the notation that's used. So when I ever say t of n, that just means the runtime. I could call it f if I wanted to, but this is just the notation that's used. All right, so what we saw with Mergesort, for example, remember what Mergesort did? What we did was we took an input of size n, let's say a list of size n, then we broke it into 2 pieces, sorted the individual 2 pieces of size n over 2, and then combined them. So the subproblems themselves, we had 2 identical, in some sense, versions of the same problem of size half of the original. So t of n for this case is going to be 2 times the amount of time to do the subproblems, which is n over 2, because the size of those problems are half of the original, so n over 2, and we have 2 of them. but there was a cost in that we had to combine the two together. So if we had two lists of size n over 2 that were sorted, what we saw was that we only needed to look at each element one time. So if we have n over 2 and times 2 elements, therefore we have n things to look at, and we see each of them one time. So what we actually do is we can actually say plus n here, but the problem is that we may need to do some allocation of a new array to put all of the new elements into, and a bunch of other stuff. But I claim that it's going to be only a constant times n amount of work. So we actually will write here big O of n. And for Quicksort, we saw something similar, but I'm actually not going to talk about that here, purely because it depends on the choice of the pivot. Okay, so it depends on the choice of the pivot. If we picked a really good pivot, actually let's talk about when we have a really good pivot. So assuming, so the assumption here is a good pivot was chosen. And by good pivot, I mean that we split the array into two pieces of equal size. Well, it's actually going to be exactly the same thing as Mergesort, because the size of the two problems are going to be n over 2, assuming we got a good pivot, and the amount of time to move all of the elements to either side of the pivot requires us to go through the whole array, which is going to be order n times, a constant times n amount of work, just like before. So the t of n runtime for this one is going to be identical, assuming we have a good pivot. Okay, so then you may be thinking, okay, well, I see that this is the runtime t of n, but I see a t of n over here. So it's like we're expressing the runtime in terms of itself. That doesn't make any sense. So how can we actually solve this? It turns out that we can do something that is called expanding the recurrence. So expanding the recurrence is a way of figuring out what the runtime is and trying to guess it and then showing that it works. So that's what we're going to do here. And since it's exactly the same between the two problems, then we're going to do that. In fact, another one that we saw was with Towers of Hanoi, but I'm going to do that one next because, well, these two are exactly the same, so we can kill two birds with one stone. Okay, so t of n is t of n over 2 plus, so I don't know what the constant is behind the big O notation, so I'm just going to call it c. That's just the terminology that's used sometimes. So it's just some number. I don't know what it is. And in fact, it won't matter at the end. Okay, so we see this right here. And by expanding the recurrence, what I mean is I'm going to expand this guy out a bit. So we note that t of n over 2, what is that equal to? Sounds like a Scooby-Doo line. Well, what we do is we actually take exactly this expression right here and just stick n over 2 everywhere where we see n. So it's kind of like if we have a function f of x and we have f of x over 2, you just stick x over 2 everywhere that you saw x before. So this, oh, actually, I forgot. This should have a 2 on the front. But that's actually crucial. So 2 times t of n over 4 this time, and I'll assume that n's a power of 2 to make this easy, plus c times n over 2, okay? Because everywhere I saw an n, I just stuck an n over 2 there. So then let's plug that back in to the top expression. Well, that's 2 times, so this 2 is mapped to this one. So then I'm going to take this guy and stick it inside here. So that's 2 times t of n over 4 plus c times n over 2. That's just copying and pasting, nothing special. And then we have this plus c times n outside here. So plus c times n. So let's simplify this a bit. So the 2 times 2 is going to give us a 4 here. So 4 instances of t of n over 4, plus, well, the 2 here gets canceled out by this 2, so we get a c times n here, and we have another c times n here. So we're going to have 2c times n. And let's expand this out one more time so that we can see what's going on. So if I expand this guy out, so t of n over 4 is just 2 instances of t of n over 8 plus c times n over 4. Again, I'm sticking n over 4 everywhere where I saw n before. So then now let's plug this back into this guy right here. So all we're doing is we're evaluating the same expression. Well, we're not changing it, but it's just we're giving it in a different form. It doesn't have a different value, I mean. So we have 4 times what t of n over 4 is, which is 2t of n over 8 plus c times n over 4. And then we have the plus 2c times n that we had before. And if we expand that out, we get 8t of n over 8 plus, again, the 4 is going to cancel with the 4 on the outside. So we get c times n on the inside, and we had a 2cn on the outside already, so we have 3cn. And we can actually see what's going on. This and this are going to be multiplied by 2 every single time. And this one's going to go up by 1 every time. And in fact, we can actually know what this is. So if this number, whatever this number is, these two numbers are going to be 2 to the power of that number. So when this becomes, let's say, 10, then these two will be 2 to the power 10, because this is going to go up by 2 every time, multiplied by 2, and this is going to go up by 1, added by 1 every single time. So we can eventually say here that this is going to be 2 to the k times t of n over 2 to the k plus k, because that's just a number, c times n. So c and k are just different numbers. C is just some number for the algorithm. K is how many levels deep we had to drill down in the recursive cases. So let's say that if we think about it for a second, at the very bottom, when we have the list of size 1, we didn't have to do anything. So that was just, say, 1 step, or just some constant amount of work. So then we can say that t of 1 is big O of 1. And if you see this, the big O of 1 just means a constant amount of work. Okay, so when we drill down all the way to the bottom, we're eventually going to have a constant amount of work. So what is the value of k then that such that we eventually drill down to hit 1? Well, it's actually really easy. All that we need to do is just to solve the equation n over 2 to the k, which is what this is. When is that actually equal to 1? So when is that equal to 1? Well, if we rearrange that, that says n is equal to 2 to the k. And if we remember our basic logarithms rules, this is saying that k is equal to log base 2 of n. And if you've done this enough, you'll notice that the 2 here is just another number multiplied by the logarithm. When you have a certain base, it's just multiplying by a certain number. So I can say that this is just some constant times log n. So big O, I could say big theta here because it actually is exactly log base 2 of n. So I could put big theta here. I just say big O because that's just what I'm used to, but you could say big theta there. Okay, so k is going to be log base 2 of n. Well, actually, let's just stick with log base 2 of n because it'll actually work easier here. So let's just say that for the moment that k is equal to log base 2 of n. Well then, putting it into the expression up here, we have 2 to the power log base 2 of n times t of, well, we know, since we solve for k such that this funny guy in here is exactly equal to 1. So this is actually 1 on the inside, because that's just what we solved it to be. Plus, well, what is k is log base 2 of n times c times n. I'm just substituting it in the expression. Well, 2 to the power log base 2, so the 2 here corresponds to the base of the exponent right here. This will actually give us exactly equal to n. Then times, well, t of 1 is just some constant, so big O of 1 is just some constant. It's abusive notation. I should put a different constant there, but this is just saying that it's just some constant times n. Plus, I'm going to actually rearrange the right expression to say c times n times log base 2 of n. Okay. One thing that we can actually notice here is that if you have big O of 1 times n, that's just some constant times n, and what we've known already is that that is big O of n. And then plus, well, this is some constant times n log n, and the 2 here contributes to the constant. So it's a different constant. It's still a constant though. So we're going to get O of n log n. So let's actually think about, can we actually simplify this further? Well, we can, because if you think about it, n log n, the relative difference between this n log n and n is growing. As n gets bigger, the relative difference is log n, and log n always goes up, although it goes up slowly, but it still goes up. So we can say that n log n is always going to be bigger than n is. So the n part is going to actually be swamped by the n log n part as n gets bigger and bigger and bigger. So this is actually equal to n log n. Okay, so this is actually the runtime of Mergesort, because that's just how Mergesort works, and Quicksort if we have a good pivot. So if we don't have a good pivot, put into the comments what you think the runtime of Quicksort is if we don't have a pivot. Okay, so let's actually try to do Towers of Hanoi, the recursion for that. So remember what we did was we had 2 moves of n minus 1 things, and what we had additionally was that we had to move the big peg once. So what we have here is that the runtime t of n is going to be 2 instances, to move n pegs. We had to move n minus 1 pegs twice, but the intermediate work is to move 1 peg, exactly 1 peg once. So in fact, we can say exactly what the runtime is, at least for this part. Okay, so then what can we actually say here? So let's expand the recurrence, just like we did before. So what is t of n minus 1? Well, we're just substituting in the expression. Wherever we see n, we're just going to put n minus 1. So here we're going to get an n minus 2, because n minus 1 minus 1 is minus 2. Again, we're going to get a plus 1 there. So then what are we going to get when we substitute back in? We're going to get 2 times 2 t of n minus 2, almost put a 1 there, plus 1 on the inside, and then another plus 1 on the outside. So then, let's see. So that's 4t of n minus 2, plus, well, the 2 times 1 here is going to give us 2, plus 1 is 3. So we're going to get a 3 there. And it's actually worth it in this case to do one more expansion. So t of n minus 2 is going to be 2t of n minus 3 plus 1 So then if we substitute this back in, we're going to get 4 times what t of n minus 2 is, which is 2t of n minus 3 plus 1 plus 1. Just similar to what we did before. So we're going to get 8t of n minus 3 plus 4 for the first part, and then 5 here. Okay, so it's actually slightly different than what we have seen so far. So let's actually try to think about what this is saying. So this is going to, oops, I didn't mean to put a 1 there. So it was 3 before, that's what was here. I made a mistake. So 3 plus 4 is going to be 7. So we can actually guess what's going to happen. So whatever this number is, this number out front is going to be 2 times as big, because remember, we had 2 recursive cases at each step. So this is going to be 2 to the power of whatever the inside number is. But look at this number out here. This is always going to, this is always going to be exactly 1 less than this. Why? Because the 2 times is going to be multiplied by the 1 here. Whatever power of 2 is going to be multiplied by 1 plus the sum of the previous powers of 2. So if you actually think about it, if you have 1 plus 2 plus 4 plus ... plus some other power of 2, the sum of those is always going to be 1 less than the next power of 2. And we can actually see that here. The next time, we're going to add 8 to this number, which is going to be 15, and then we're going to add 16 to 15, which is 31. Again, 1 less than a power of 2, and you can prove that formally. So if we expand this out, what we're going to get is, for some number k, it's going to be 2 to the power k out front, plus 2 to the power k minus 1. Okay, so what do we actually need to solve here for? So we need to think, what is the runtime for moving 1 peg? So what is the runtime for moving 1 peg? So let's say that takes exactly 1 operation. We could put O of 1 there. It turns out it won't make a difference, but let's just say it's 1. So let's substitute in this expression when k is exactly n minus 1. Okay, so when k is equal to n minus 1, then that means we have 2 to the power n minus 1 times t of 1, because we're just substituting k equals n minus 1 up here, plus 2 to the power n minus 1 minus 1. Okay, so then what do we get here? Well, t of 1 is just 1. So 2 to the n minus 1 plus 2 to the n minus 1 minus 1 is what we get. And if we add 2 powers of 2 that are the same power, then we're going to get the power more than that. So this will actually give us 2 to the power n minus 1 steps. Okay, so that is actually the runtime for the Towers of Hanoi problem, which is considerably more than what we got for merge and for quicksort, assuming that there's a good pivot. Okay, so there is a formalized way of doing this. In fact, there's a generalized way called the master theorem that will eventually show how to at least intuitively see at some point in this series. But for now, this is just a long intro to asymptotic analysis. So the relative difference, we're measuring the relative difference between 2 algorithms, and whether one is, the relative difference is growing bigger than another one, or whether they're growing exactly the same rate, or one's decreasing or something. And what we were able to do is do something called guess and expand the recurrence. I should have called this expand. Yeah, guess and expand the recurrence. And by doing that, we can actually determine the runtime of various algorithms, such as Mergesort and Quicksort and the Towers of Hanoi problem, which, even though the runtimes may look scary because they're defined in terms of themselves is actually really easy to solve, and there's a very intuitive reason why those algorithms have those runtimes. So hopefully that was interesting. Leave a comment down below if you have any other interesting thoughts about this. As always, please like and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to contribute to the channel, such as donating or joining our Discord server. And as always, I'll see you next time.